Okay, so this is a continuation of these pumping problems for calculus 2. Let's look at a different shape. Let's look at a cone, okay? So we have a conical tank here, all right? Let's make the radius at the top 8 feet. Let's make the thing 20 feet tall, okay? Goes down to theoretically a point. And let's say that we're going to use our pump here to pump the material out 12 feet above the top surface of the tank. Okay, so the discharge here is going to be 12 feet above the top surface of the tank. So remember that we get this for free, this fluid in here. Let's give the density 55 pounds per cubic foot. So we get this fluid flow for free. Okay, so we start out here. So our integral is going to go from where to where? Well, we're going to start lifting it at y equals 12, right? And by the time we're finished, this is 20 feet. So it's going to be y equals 32 feet here, right? So we said that work, which is what we're after, this is force times distance. We've already got our distance. That's our distance, okay? Now we need our force. So force is going to be, again, volume times density. And basically what we need is we need the volume of a layer of this fluid, okay? And the volume of this thing, this again, just like in the previous problem, this is going to be dy, okay? So our volume is going to be pi r squared dy. Now, notice that I didn't put an r in here because the r at the top is 8 feet, but the r at the bottom here is 0. So the radius changes as we're pumping down the tank because it's a cone. So since this is now a function of y, we can't use it as a constant, okay? So we're going to have our density here. We're going to have our pi, okay? But in here, we're going to have a function of y that represents the radius. We're going to have to square that, okay? And then we're going to multiply that by dy. So this is going to be our force term, right? This is our distance. Force times distance is work, okay? So the question is, what's the radius? Well, a quick way to get the radius is to notice that, first of all, it's a function of y, okay? Because as you go down in y, your radius changes, right? So we can make a chart, just a simple chart, okay? So when y is 12, we know that our radius is 8, right? And when y is 42, no, wait a minute, what is this, 20? It's 20. When y is 32, the radius is 0. So when y is 32, our radius is 0. Also, look at the sidewall of this tank, okay? You see that it's a line, right? It's a straight line. So this has to be a linear relationship. So we have two points here, basically, right? So we can get the slope of this linear relationship pretty easy. It's, okay, so now, you know, with the slope formula, right, it's y2 minus y1 over x2 minus x1. But y in this thing is a function of x, right? So in this case, it's going to be, in our case, it's going to be r2 minus r1 over y2 minus y1 because of the variables that we're using here. Yes? So r2 is 0 minus r1 is 8. y2 is 32 minus y1 is 12. Okay? So we're going to get negative 8 over 32 minus 12. That's 20. So that's negative, what? 4 goes into that 2/5. Okay, negative 2 over 5, right? So we know that r, as a function of y, is going to be negative 2 over 5y plus some constant, right? We can get this constant by plugging something in here, yes? So we know that r is 0 when y is 32. So we get negative 2/5 of 32 plus b, yes? This is going to be 64 over 5. So b has to be 64 over 5. So our radius term here is going to be negative 2/5 y plus 64 over 5. So now, you know, we can square this, distribute, and we end up with an integral of a polynomial. Not too bad. But that's how you would handle this with a conical.